Okay, good morning, everyone. So we have now heard a bit about extremely small satellites. And actually in Luxembourg, we were also curious about what we can achieve with this very small spacecraft. But right now, I know that there may be a question you may all have, which is what and where is Luxembourg? That point in the middle is Luxembourg. It's actually bordering France, Germany, and Belgium. And it's a very small country, but it's actually a financial center in Europe that started making its wealth through producing steel, but now it's mainly through private banking. There's 3 official languages, which are French, German, and Luxembourgish, but the population is 47% foreigners, so when you walk around, you hear many different languages. It's also very important for us today, an aerospace hub. There's now over 20 startups and companies in the industry, and the Luxembourg Space Agency was founded in 2018. So the industry in Luxembourg is really growing a lot right now. We work in the University of Luxembourg, which is oriented mainly towards research. So if you look at the students that work there, you will see that they are mostly PhD students. And it's a very interdisciplinary atmosphere. It's also, as I mentioned, Luxembourg is very international, so the university is also international and multilingual. You find people from everywhere. It's conformed by 3 faculties and 3 interdisciplinary centers, and we work at SNT, which stands for Interdisciplinary Center for Security, Reliability, and Trust. Now, there's 4 other subgroups in this center, but we work in space systems, and we are the Space Systems Engineering Research Group. We were created just last year in September, and we do work on end-to-end mission design. We start with mission concepts, and we go all the way to verification and testing in orbit. So we have heard that there's miniaturization. We know that miniaturization of electronic components has enabled miniaturization of space systems, and we started with microsatellites, going all the way down to nano and picosatellites, which is where you find PocketQubes. But as we already heard in the previous presentation, we can even go further down to femto and attosatellites, going all the way down to 1 gram. And that's where we work in Luxembourg. We work with chipsets. They can fall in either femto or attosatellite category, depending on their mass. And you can see 2 examples there. So they're basically, a chipset is a flat satellite, 10 by 10 centimeters in dimensions, but you can go all the way down to maybe 2.5 times 2.5 centimeters. So basically a PCB. But why do we want to work on this very small spacecraft? We already have PocketQubes, which give you even lower cost, lower mass than CubeSats. Well, with chipsets, you can get even lower cost than PocketQubes. You can go with 2 lower masses. This means, because they're very small, you can develop them very fast in a matter of 6 months, even less maybe. So if you launch large numbers, you can create large constellations or swarms of these very small spacecraft. And we also believe that they will enable access to space even further than currently to countries that have low resources.
Yeah, thank you. I hope I don't fail with this. Okay. So this is a slide that contains a few of the chipset concepts that we have already seen. They range even in the past decade. We've seen some concepts from 2009. And you can see on the bottom right, I have respectfully stolen the image from Thomas from the previous presentation. But these are not flown missions, not all of them. These are mostly concepts or ideas. Some of them have been in balloon flights, so they have been tested. Some of them have actually been to space, so these missions, these chipsets, have actually gone to space and have actually had quite successful results from the past years. And I remind you, these are all spacecraft that are smaller than 5 by 5 centimeters. So in the University of Luxembourg, we do, in the Space Systems Group, we want to do some high-level research on those concepts. And in order to do that, we thought that it would be a good idea to also develop a tech demonstrator of our own. So this is our tech demonstrator. It has the very original, very inspired name of ChipSat-1. And this is how it looks like. So as you can see, it's a distributed system. It's a fractionated system. As it is a technology demonstrator, it's just a very, very small count of parts that we have. So one primary and two secondaries. And the idea is that the secondaries gather data, gather the science data. They transmit this data through an inter-satellite link to the primary, and then the primary transmits the data back down to Earth. The interesting thing that we do is that we don't do the inter-satellite link with radio frequencies. We do the inter-satellite link with LEDs, with light-emitting diodes, so visible light, not laser. And this is just a tech demo to see how easy this is to do, what kind of data rate we can achieve, how much ambient light, that is the sun, how much it can affect our results. So we generate data in the secondaries, we transmit this data to the primary, and then we send this data back to Earth. And we have visible light for the inter-satellite link and RF for the normal ground transmission. Now, when we came up with this concept, we tried to find a launch opportunity to get any way to get our spacecraft down to up to space. We figured that the easiest thing we could do was to just combine all those different parts together into a single PCB. But still, the three parts, so primary to secondaries, are still completely independent, electrically independent. They just have the same structure and only the light that's communicating between them. Some statistics, some numbers. So the dimensions are 5 by 5 centimeters for the entire thing. The mass is a bit less than 30 grams. This is actually considered a lot for this class of satellite. Manufacturing costs about 2,000 euros. Component cost is about 1/10 of that, so 200 euros. And for communication, we're using UHF with a power of about 100 or more milliwatts. The sender of our primary is a system on chip, so an ST microelectronics microcontroller that has an integrated RF transceiver inside. So this let us save quite a bit of space because comms and processing are integrated into a single package. We don't do custom chips yet, but this is something we would like to see a lot. As you can see, this thing has 4 mounting holes on the edges. This is because it will not be free-flown, it will not be deployed. It will be mounted on another spacecraft. We are looking forward to a future mission where we can deploy something and have it free-floating in space, but not this one. And we are actually planning to launch this next month. We are in contact with a company. We're in the process of signing a contract. And yeah, this means that we are very tight on our schedule. We are actually waiting for the flight models to be manufactured and sent to us. And we are aiming for a launch in October next year. And just to prove to you that we are actually working on this thing, this is a photo of our engineering model, and you can see that in the middle there is this green LED that's blinking and sending data digitally to the primary. Now the LED and the photodiode are very close in this scenario, but we just wanted a very quick, a very cheap tech demo that we want to send to space, and this is how we achieved it. Now, just one small technical detail before I move on about power. So, very small dimensions, very small surface for solar panels. We have about 100 milliwatts that we can get for the total structure. Also, the temperatures get very low, which means it's not straightforward to include batteries. What we do right now is we just have a small capacitor, and I mean, that's actually a large capacitor, but anyway. And we basically can only operate during sunlight. Now, we've been working on this mission on and off for the past 1 year. It's been 2 to 3 people that have been working on this. It's been an interesting journey. We've learned a lot of interesting things. For example, the design drivers our design was not based around what we needed or what our requirements were. Our design was based around what we were capable of and what other people could give to us. The cost can actually become very low because it's just the cost of manufacturing an IC. If you can do it in-house, it gets even lower. And then there is the cost for whatever environmental verification you need to do, whatever your contractors require, so vibration, thermal vacuum, EMC testing maybe, I don't know. Depends on how you're mounted. And we also had some unexpected issues, typical procurement, logistical delays, and also a lot of changes in interfaces and requirements from our partners. Because this is a quite new area, there is no standardization yet, so everything is prone to change. Which means that we basically need to be very responsive to changes. It's an interesting design process because you almost know nothing beforehand, so you need to be able to make design changes in just one day. And this creates interesting problems for documentation because you need to keep everything pretty much up to date.
Thank you. Oh, sorry. Okay, so what our team is currently working on is thinking about what are we going to do in the future, which will be our next mission. And for this, we have started with some brainstorm sessions to get some new mission ideas. And we have tried to categorize them in different subcategories. And we will use them as input to create this matrix for an analytic process, a hierarchy process. And then we will apply certain decision criteria to this process in order to be able to decide on our next mission. And then in this mission, we hope to be able to apply the lessons that we have learned from Chipset 1. So for this future mission, we are thinking of maybe continuing work on chipsets, maybe during the next iteration of Chipset 1. But another possibility is moving towards PocketQubes. We know that they are different. Of course, they are different configurations, and they also offer a different set of missions that you can achieve. But we actually believe that there may be some complementarity between them. For example, they achieve different missions, but at the same time, these can complement each other. We also have some issues with the chipset. Finding launch opportunities is quite difficult, but we believe we can use the structure of a PocketQube, attach a chipset to each phase, therefore having 6 chipsets, and that would make it much easier to launch. We also think about complementarity in terms of methods. So we believe that we can apply the method that we have used to develop the chipset to start developing our own PocketQube. So to conclude, we want to leave you with chipsets give us massive redundancy. As we know, we can launch lots of them, so that will help us have these big constellations. We believe also that they will open the doors even further to space, to countries with low resources, lowering this barrier that lots of them still have because they can't even afford a CubeSat, not even a PocketQube. These rapid iterations are possible due to the very fast development, and we also believe that Pico, Femto, and Atto satellites have some common ground, as I already mentioned, in terms of mission, in terms of technologies, in terms of the standards that we can use to benefit from each other. But in the future, we also want to think about even more unprecedented missions. For example, start going into deep space. We are also looking into new launch opportunities, finding different ways to launch our chipsets. And we also want to start building this community around chipsets like we have here for PocketQubes, but now for chipsets. So thank you very much for your attention. If you have any questions, we are happy to answer them. So thank you.